What's up, guys? Welcome back to another episode of the Traders Brawl podcast. I'm Adel, I'm the host, and this podcast is a podcast for entrepreneurs, a voice for visionaries, and for learning about new trending insights. Today's guest is Martin Vogrin from Slovenia, who will be talking about quantum computing, which is an area I feel that I have very little knowledge about, and I'm really excited for our new guest to enlighten us about this new information. And without further ado, we're going to get to this. But quick introduction about Traders Brawl. We are a platform, a voice for entrepreneurs, but also fitness with financial freedom. So we always invite people who are in the fitness space and want to share their tips and tricks on how they maintain a work-life balance alongside their hustles, their work hustles. So let's get straight to it. Martin, and please introduce yourself.
Yeah, it's great to be here. I'm Martin, and I'm the CEO of TipQC. We are a startup developing quantum computing algorithms especially for graph analytics.
Okay.
And we are currently based in Dubai here, but we have another company in Slovenia. We do some IT consulting.
Nice. And so just a quick introduction for the audience. We met at this event by Christine at TipQC at one of the NAS villas. That was an interesting night we met. What were you doing there?
I just moved to Dubai, and my main goal is to expand the business. So it was a networking event. I wanted to meet new people. I met quite a few very interesting people, you included.
Right.
I just want to meet as many people as possible, hopefully in the tech space, in the entrepreneurial space, and see if we can build something together.
Brilliant. So let's get straight to it. Martin, what is quantum computing?
All right. So I guess start with the setup. Right? Let's say you have a picture, right? And on your phone doesn't know what a picture is the way you know what a picture is, right? The way your phone recognizes or stores the pictures is as a set of zeros and ones, and all the other data, right? It's zeros and ones in a sequence. Right? And then let's say you want to make operations on these pictures, like turn it black and white. There's an algorithm that turns some zeros into ones and some ones into zeros, right? That's how classical computers work. And now researchers developed a new type of computer, which is based on like very small particles, where you, instead of zeros and ones, which you can think of as a light switch, right? So you have one if the light is on, you have zero if the light is off. You have something like a slider. So you put it up and the light turns on a little bit, or you turn it down and then the light goes off, right? And then now the question is, how do we develop algorithms, for example, for making picture black and white, right, where you flip some zeros into ones and one into zero, where you have to adjust the sliders. So that's one aspect of it. And another aspect that I would like to introduce, but it's a little bit more nuanced, let's say, is what's called entanglement. And that is that these sliders, they're connected to each other, right? So the zeros and ones, they're disjoint. You turn one zero into one, or you measure it, it doesn't affect the others, but the sliders, they're somehow connected. And this is what it's called entanglement. And it's in fact this entanglement that makes quantum algorithms potentially faster than classical.
So what problems does quantum computing actually solve?
Well, currently, it's trying to solve problems where classical computing has problems, has issues. That means anything that's very complex, anything that's very computationally demanding, it might be a good idea to try to put it on a quantum computer to make it potentially faster. Now, current use cases are sort of like in logistics. So logistics, it's a very complicated system, right? Very expensive to run computations on them, doing problems in logistics like optimization. That's a very interesting area. Search on relational databases. Of course, very relevant in the media and elsewhere is encryption, and cryptography. And then also you can run most of machine learning algorithms that you can run on classical computers, also on quantum computers, and hopefully make them faster as well.
So the realm that I know quantum computing in is mainly in the encryption side of things, which helps with cryptography and blockchain technology is used in that because it's it helps protect the data and privacy of the user, and many banks use quantum computing for that reason. But I'm aware that it also solves much more bigger problems than this. That's why I wanted to have you on the show. And I'm sure many people in the audience don't actually know what is quantum computing. They just maybe know binary code of ones and zeros, and that it's not the same as a supercomputer or a normal computer. It solves much bigger issues, but to know what exactly they do, things like entanglement, we need more insights on this, I feel.
Yeah. All right. I mean, so entanglement, you can think about it as in sort of a way where let's say you have a piece of paper and you tear it in two, and then you put it in two boxes. Right? You open one box, you look at the piece of paper, you know immediately what's in the other box, right? Because it comes from one piece of paper. Right? So this is sort of the idea of entanglement, and this is really a crucial concept in quantum computing, because everything else, like the picture that I explained with light switches and sliders on the other hand, dimmers, that is just a technicality of how you store data. But entanglement is the thing that really makes quantum computing faster. So the ability that you don't have to look at each bit, 0 and 1, one by one, but you only look at the subset and you know all the information about the system. This is what makes it really faster. But let's say you want to analyze, I don't know, even just sales forecast. This is something that is so simple to do, and we can do so much on classical computers in terms of machine learning, in terms of optimization, that it doesn't make sense to put it on quantum, because you need all this infrastructure, quantum computer somewhere which costs trillions of dollars to build. You need hard problems. You want hard problems to put them on a quantum computer.
Right. And as I understand it, with quantum computing, you can solve, you could probably hack into and decrypt data sets much faster than a normal classic computer. You just need one, you may need a few things, but it may take, as I understand it, you would have to run lots of combinations in a classic computer to find out what's the code, to crack the code, what's the password. But with a quantum computing, it can do it in maybe a couple minutes. Is that correct?
That is not completely correct.
Oh, okay.
But I mean, it is the right direction. Yeah.
Right.
So the way most algorithms function, or like post quantum, so classical algorithms function, is they encrypt data with something that's called a public key, and then you also have a private key.
Right.
And a public key is essentially a product of a private key and some other prime number. And the security of this whole system is based on the fact that it's very difficult to factorize this public key into private key and the other part.
Right.
And quantum computers, it turns out, they're more efficient at doing this factorization. And this is why classical encryption methods are a little bit in jeopardy. However, to actually do this on a 265-bit key or whatever we have right now, current quantum computers cannot yet do this.
They cannot yet do this?
No, not yet.
Oh.
Not yet. So the problem is in the speed the quantum hardware is developing. So if you look at the history of hardware, it typically follows an exponential trajectory in development. So even 5 years ago, we had maybe 10 qubits or so. Now we're talking about 100 qubits already.
Right.
So it's really an exponential growth. And the issue is, what if there's a quantum computer we don't know about?
And that's possible that they're running dark
somewhere
things
in a basement. That could crack
our encrypted, what we think is encrypted.
Exactly. Yeah.
Oh wow, that's very scary.
Or in 5 years, when there will likely be one, then we have to be prepared for this. Right?
That is so scary.
Yeah, I mean, okay, it's maybe a little bit of an exaggeration.
You mentioned qubit, so I understand that a bit is the lowest size that a classic computer can hold in terms of data. So please explain, what is a qubit now?
So a qubit is a quantum version of a bit.
Okay.
And the way I like to think about it is really like as a light switch. So bit is 0 and 1, and qubit is a dimmer. So it's something between 0 and 1.
0 and 1.
Exactly.
Between.
And you sort of slide it. It can be 0.4253
right.
And so on, right? And it gives you the probability that all right, so let's say there's a room and there's a door, right? You turn on the light switch. You go into the room, you see the light is on, right? You go out, you turn it to 0, you go in, the light is off. You know exactly what's going to be, right? And for a dimmer, you set it to some number, and that's the probability that when you walk into the room, the light is on or the light is off. Right? And so this is sort of how qubits work. They have a probabilistic nature, and they're sort of continuous between 0 and 1. Right? So you set them. And yeah, they mimic essentially, so more technically, the implementation mimics what's an atom. And so atom has certain energy levels, and you have electrons that circle around the core, and then you can excite this electron, right? You can put it to a higher orbit and so on. And all the implementations sort of try to mimic that. So the lowest orbit is 0, the higher orbit is 1, and then you typically stop. But you can also have more, so you can also go higher, and you would call this D-level systems.
And apart from what I mentioned about encryption and things like this, what are some other use cases of quantum computing?
Well, most interesting. So some of the most interesting use cases come from areas which are close to quantum in nature. And what I mean by this is something like quantum chemistry. When you have data that comes into quantum computing which is already quantum. It's already on a small scale.
So when data is in the computer, you mean, or where?
Right. So the data is not even stored as zeros and ones, but it's stored directly as a quantum measurement. That's ideal.
Okay.
That's ideal because so this encoding of classical data into quantum, that's actually quite challenging to do.
I see.
Right? But so if you can get quantum data, that's ideal. Then, use cases, quantum chemistry, certainly huge area for quantum computing. So how to find new molecules, new drugs, new compounds, and so on. Right? Then
so you can identify these?
Right. You can
on the computer, or
right. You can build them. So the question is, let's say you add a molecule, where is it gonna attach? For example, to a big compound, right? Or what are the properties of certain compounds and so on. Right?
Understood. And with quantum computing, does it operate like an interface, like a normal classical computer? Can you see? Is there an interface, or no?
Yeah. You build an interface. So quantum computers are typically in the cloud. So you have to send data to the cloud, then you get the data back, and how you interact with quantum computer, it's very similar to.
So no classical computer.
Exactly.
That's what I assumed. But the main action, the activity that takes place, is in the cloud, because it's working with data all the time.
Right, because quantum computers are expensive to build and expensive to buy. Right. So most companies do not have their own quantum computer.
Do you have one by any chance?
No, we don't. You can buy it. I think. A pretty powerful one, like 10 qubits. You can buy it for $900,000, something like that. That's the price of it.
Okay, wow. Interesting. So now let's move on to TipQC, which is your company. Give a brief about what is it that your company does.
So what we do is we focus on using quantum computing for machine learning on graphs and more general graph analytics. Got it.
So in terms of that, what is graph data, and why is it important for businesses today?
There's a lot of graph data. A typical example would be social media, like Facebook or Instagram. So the people you follow or the people you're friends with, they form a graph.
Right. You can see the...
Exactly. You have nodes, which are people, and then you have connections if somebody is a friend. Right? And I mean, there's two features, or maybe three features even, of such data that are very well suited for quantum computing. So if you just look at social media networks, right? Of course there's many others, but social media, you know, it's huge. You know, so there's huge amounts of data. It makes sense to use quantum, as I said before, right? Because it's a complex problem. Two, graphs are very complex. Like, even if you just look at your own social network, you will see that, you know, it's hard to handle. You know, it's hard to even imagine. And then you think about the next step, how many friends your friends have. It's huge already, and it's very complexly interconnected. Right? And this is also something that's very interesting for quantum. And the third thing is that these networks change all the time. And so you're adding new nodes, you're adding new connections, and so on. So it's not something that you just run once and then you let it be, but it's something that you have to run continuously. Sorry, to return to the first part of the question. So graphs, you have social media, of course. You have recommendation engines, or like links between, if you watch Netflix, you know, what movies you watch and how are movies connected to each other. So the Netflix will recommend movies for you, for example, based on graph analytics. Like road networks, you have intersections and then you have roads between networks. And Google Maps, for example, uses graph analytics to recommend the best route.
Is that all quantum computing, or?
No, they do it on classical.
That's what I thought.
But again, what all these things or all these use cases have in common, it's huge data, it's complex connections between, you know, different nodes, and it's constantly changing.
Right. There was a phase an era, should we say, that we were in, this whole big data era, which I remember studying when I was at university. So this big data narrative was that they analyze your data and then personalize it based on your actions, right? So nothing's too different from graph data, right? Because graph data is analyzing and then producing a personalized approach based on what you have done. Right. Is that what you're doing at TipQC?
Yes, to a large extent. The question is just how this big data is organized. Right? Because you can have big data which is in forms of images, in forms of text, in terms of tables. What we look at is really this data which is interconnected between each other.
I see. So what would be a typical client of yours?
All right, so what we're focusing at the moment, especially on, and this is one that I didn't mention under graph, is analytics of relational databases. So what is a relational database? You have a data table, let's say users or customers and so on. And then you might have a different table which has products. I don't know, like Amazon, for example. Right? And you might have channels like, did I buy it over my phone? Did I buy it over the computer? But these are all connected because I bought a product, so I'm connected to a product, and you bought a different product, so you're connected again to a different product through a channel. You know, so it's a graph. You can turn a relational database into a graph. And what we're trying to do is we want to do machine learning, large-scale machine learning on big data, with turning a relational database into a graph, and then running quantum graph analytics on it to get information about databases. So coming back to the question, who's our client? Our clients are companies who have big databases. So it makes sense to put them on quantum. And this would typically be banks, this would typically be telecommunications companies, or any type of retail operations. That's what we focus on especially.
And then the sort of outputs from doing all this work, what sort of outputs can they expect?
There's a lot of use cases, as you can imagine, because it's really like, it's machine learning on a relational database. Now, it's how all the data is structured. So you can, for example, do segmentation of customers, you can do channel analytics, you can do product analytics, like how to construct bundles in a good way, where to give discounts, how to apply marketing campaigns efficiently, right? You can do churn predictions. This use case is, again, focused mostly on retail analytics, but it's machine learning on relational databases. You make up a business case, it's probably analyzable in this way.
And is it analyzable without the use of, because we already identified it, without the use of quantum computing, it can be analyzed.
It can be.
It can be. What is it that that TipQC does that's different, would you say?
Well, there's essentially two ways that you do it right now. One is when you have this data tables in a relational database, you just glue them together. But this is a long process. You need consultants. It's complex. There's human input, and I think it's just not the best way to do it. I mean, it's very useful in some cases, but I think there's better ways. So you can also do what I just described. So you turn a relational database into a graph, and then you run machine learning on it with classical computers. No issues there. And I think it's excellent. So it's a very recent development. I'm very happy about it. But graph analytics, as I was sort of trying to say, is it's very complex. Graphs are complex objects, huge objects with a lot of data. So if you want to run this constantly, fast, accurate, cheap, it makes sense to look into quantum. It's an excellent use case for quantum.
And just curious, are you in competition with Google? Because doesn't Google provide these services too, especially with Google Ads?
Yes, maybe.
Yeah, because they give you analytics based on your ads.
I'm not sure how Google Analytics works, if it really works with analyzing these databases, or if it makes the master table and then analyzes the table. I'm not completely sure about this, but I'm pretty sure they still do it on a classical computer.
Yeah.
So we are hoping to beat that.
Of course.
That's the goal, right?
Right.
Put it on quantum, make it faster, make it more accurate, make it more efficient, and hopefully you work together with them, integrate it.
When it comes to putting it on quantum, like you said, and you said you don't own a quantum computer, how do you actually put it on quantum then?
Very good question. Very good question. Very complex question. So the short answer is it's very simple.
I love that.
Yeah. You go online, you rent a quantum computer, and then you just make a call. It's like classical. It's like renting a supercomputer. It's like renting, any other processing space.
And they're cheap to rent or expensive?
They are comparable to supercomputers. So it's between 3,000 and 5,000 euros per hour.
Oh my God.
Yes, but in an hour you should be able to do a lot. Right?
Wow.
So it's about as expensive as renting maybe 10,000 GPUs, which is a large supercomputer.
Right.
For machine learning. All right, so to maybe elaborate a little bit why this is complex is, simple implementation. I just want to run some code, quite simple. If I want to implement this at a bank, this becomes much more difficult, right? Because first of all, if you rent a supercomputer, there's always space available, and it's sort of well known how to do this. Right? For quantum, you have to negotiate a little bit how much space you will have at a certain point, how many qubits you can use, and so on, right? Because everybody else wants to rent the same quantum computer, and there is not that many yet. Right? So this is one issue, and the other issue is, especially if you work with big clients, quantum computers are in the cloud, almost exclusively, and big banks or big telecommunications companies might not want to put data in the cloud because of
hacks,
security concerns, information concerns, and so on. So you really have to make sure that this data is encrypted, that this data is anonymized, that the security is there, and that is something that you have to work on and you have to offer if you're working in this space. I believe any quantum software company should have some mechanisms in place for this.
Understood. Wow. Okay. So back to TipQC. What are some of the biggest challenges that you say that you as a company have faced when considering, adopting quantum or considering how to solve a client's issues?
The biggest challenge in quantum is always hardware. No question about it. If we can solve hardware, we can solve everything else. And I mean, what I like to say is that right now we are running quantum algorithms on quantum calculators. So we have 50 qubits currently that are available, something around that number. Right? So 50 qubits, 50 bits is really, it's less than what a calculator has. And we are trying to beat classical machine learning or classical optimization algorithms on calculators. Now that's the game that we are in. Right? So when we work with clients, right, we need to make sure that the software that we build will be usable when the number of qubits increases. When the power increases, they don't want to rebuild their whole software. So we have to do this on one hand. The second thing that we have to deliver is that algorithms that we develop are useful right now. Mm-hmm. Right? Because typically banks or telecommunications operators or whoever the client, they have some algorithms. They will not hire us if our algorithms are just worse. Right. And now they have to rent a quantum computer in addition to what they have, right, to get a worse result. So we sort of have to beat their algorithms, or at least we have to have a roadmap how, when quantum hardware develops, we will be able to beat the algorithms, or in some aspect. This might be accuracy, this might be some different insights, it can be speed, cost, or so on. In some aspect, we have to beat them. I would say that's the main problem. Yeah, how to work on this limited quantum hardware and deliver value for the client.
Right. And curious to also ask, at this stage in life, are you using any AI technology to help with your ability to deliver to clients? Well, I mean, it's together. You're using machine learning as well, but are you using any AI tools to help with the processing of all the data?
We are actually developing AI. So we build quantum machine learning algorithms.
I see.
That's essentially what we do. I mean, there is a graph analytics standard, but we also use machine learning on graphs. That's what we're building. And we typically build classical machine learning on graphs. We build quantum machine learning on graphs, and then we merge them, and we build hybrid models. And so that's the standard right now in software development in quantum. Typically, you build hybrid models that have classical machine learning part, they have quantum machine learning part, and then you merge them together and so on.
And who would you say? I know you mentioned your clients are typically banks, these kind of people, but can it also work for retailers? Let's say they want to analyze their graph data of their their community. Could this work?
Yeah, certainly. Certainly, the only caveat is what I mentioned before. If you spend, I don't know, 1,000 euros on data processing every month or every year or whatever, it doesn't make sense to put it on quantum. It has to be big enough. If you really want to understand your customers better, and you know that this will drive hundreds of thousands of euros or millions of euros in revenue, then it makes sense to put it on quantum. Right? If you are doing small-scale analytics, just use classical machine learning. It's good enough.
It's good enough to analyze it and give you the best outputs possible.
For almost anything. You really need big problems for quantum. Yeah.
I see now. Awesome. Very nice. Very interesting. Talking about security, because security is a very important concern for many businesses and retailers too. How does TipQC ensure the security of its clients and processing sensitive data on quantum?
We are a little bit lucky, I have to say, because we deal with graph data. And so graph data, it's a little bit easier to encrypt than other types of data. Right? So other types of data, of course, you have methods to anonymize and to secure it, but with graphs you can go even a little bit further. So you can permute the graph, you can split the graph into subgraphs, and so on, right? So you sort of encode part of the data, which is connections, and then for nodes we typically would use classical techniques for encryption.
I see. So the graphs has already been has it already been anonymized since you're already working with graphs, or no?
No. We just turn data into a graph, but then in a graph we have quite a lot of freedom of how we can change the graph.
You can change the graph.
Exactly, yeah.
Now this raises another concern for me, because you know how you can manipulate data. So you can also manipulate how the graph looks. Is that possible, right? So that means, when things like campaigns like Brexit and riots that happen, you look at the data and you put out an ad saying NHS is costing 80 billion a year, and you can show that on the graph when it could be false. What do you say to that?
It's so interesting. Like, this whole area is just extremely interesting. Like, I think what you're talking about is influencers in the graph. So, for example, on social media, right, you have these people like Cristiano Ronaldo who have billions of followers, right? And then when you run marketing campaigns, you want to pay him, right, because he will influence so many others. And if you pay, I don't know, my neighbor or a random person, they will have much less impact on the graph, because of how it's structured. So, interesting problem, for example, for graph analytics is like who you should pay. Because for the amount of money you pay to Cristiano or other influencer, you could, maybe pay 1 million of less known users who will have a larger impact on the graph. Things like that, extremely, extremely interesting. Or what happens tomorrow if we remove one of these influencers from social media? Like, I think Trump was banned from Twitter.
Right.
What happens? What happens now with these opinions? What happens with the graph? How is the opinions distributed now? Who becomes the next influencer? Extremely interesting stuff.
Yeah, and it is possible to manipulate the people's decision making as well when it comes to voting, which president to vote for based on the data that you showcase them.
Right, 100%. 100%.
It's very scary.
That's one, and the second one, which was also in context of elections and influencing of decisions. Which actors in a social network are bots? How do you identify this?
Which actors are bots?
Yeah, which members of which accounts on social media are fake accounts, right? Bots. How do you identify them? They have some particular patterns. They maybe have some particular connections, and graph analytics can help with that.
Oh, that's an interesting one, because that's probably a use case for me, because I get a lot of fake followers and also fake impersonators that clone my account and then produce content on my behalf.
Right. Yeah, interesting. Again, I'm not sure if it's a use case for quantum. Maybe you want to use something else, but Twitter, for example, certainly would be interested in having a technology where they could identify bots.
Right. Have you ever identified bots before?
No, we haven't done that yet.
Okay.
But I think we could do that.
All right. No, very interesting. Very nice. And curious as well now, when it comes to onboarding a client, just walk me through how TipQC goes through, onboards a new client. How do they go through that process and then have them as an official client?
Well, I think what you want at this stage in technology is that clients have somebody who's a technology enthusiast a little bit. So he's or they are on their own excited to be a part of this and to develop quantum applications and to learn about it, because it's still like the whole industry is essentially in a learning process still. As I said, we are very close to performance of classical algorithms, but we are not outperforming them by a huge margin. And nobody is. But we will. I'm pretty confident that we will. So you want somebody who's a technology enthusiast who will sort of keep up the motivation of the team, right? And then we make, like any software development project, we make a roadmap, we prepare specification. What's maybe a little bit specific is that we typically want to develop classical models or see what the client has in terms of classical models. And then the hard work begins, which is beat the classical models with quantum. Right? And then we work with the client to define the use cases and build the software that does what they need it to do. And then we test it on a quantum computer and turn it into SaaS or into an operating software. But yeah, so it's very important to identify use cases well. Like having a large enough impact for quantum to make sense.
Right.
That's certainly something. Having this future-proof characteristic that it's going to stay and it's going to scale. Those would probably be the main factors here. And then build the software and deploy it.
Right. And typically, how long does a project last? I mean, I call it project, but you may have another word for it. How long does a client project normally last?
Well, if we just want to test it out, see how it is, then that would probably be between 2 and 4 months.
Okay.
But then a longer project could be anything between 9 months and 2 years.
Right, of course.
To do like more specialized development for certain use cases and so on.
And there, like you said, their database has to be fit for purpose in order to have quantum, to be fit for quantum. Typically, what's a database size? That's a rule of thumb that you like to work with.
250 terabytes, something.
250
like that.
terabytes. Oh
yeah.
my goodness! Wow. I've got 1 terabyte. I've got 16 terabytes on my hardware for all the content that I produce. 16.
Yeah.
But you're talking 250,000 or 250?
Terabytes. But so the difference might be that your content is mostly videos and pictures, and that's heavy.
Yeah.
What we're working with typically is more data tables and text data, which is less heavy. So
less heavy, but
more,
still a lot.
Right. I mean, it's more of it because it's less heavy. Yeah.
Right.
So it needs to be large to make sense.
Right.
Otherwise, just do classical.
Classic is enough to do it.
It's enough.
Right. Awesome. And just to go down the classic route, typically, how would the classic route look like? How do you process it?
I mean, typically for graphs, there is machine learning models that work on graphs very well.
So Excel?
No, not for graphs.
Not Excel.
Not for graphs. For graphs, you typically use some software.
Okay.
Specialized software.
Okay.
You develop it, or you use some libraries that are out there.
Right.
Like PyG, for example. It's very known.
So you input the data in PyG, and then it does it for you.
Exactly. Yeah.
Okay.
Or and then you tweak it, but yeah.
And it has machine learning algorithms inbuilt.
Yeah, right.
Right. And then you can produce. It's sort of like SQL, but that's searching for data. But in this case, you can get actual insights from the data that you inputted by typically typing like, what does this mean, or how does this work for me? How many clients bought X amount in this period?
Right. That's exactly how it should work.
Understood. Wow, interesting. Okay, now going into the future, like quantum computing is a very evolving field. I want to know, where do you see TipQC in the future, in this realm of ongoing evolving of AI and machine learning?
I'm quite a fan of AI, and I want it to do even better. Like there's a lot of investments right now in hardware in AI, and I want it to be faster. I want there to be better models, and then what I would personally really enjoy doing is then building quantum models and beating the classical ones. Now that's the goal. The goal is always beat classical models in one of the aspects, like accuracy, speed, cost, whatever, but beat them. Right? So what I see is going to happen is, right now, I think OpenAI is asking for $2 trillion of investment, and they want to build hardware. That's the main focus where the money will go. If you look at NVIDIA stock, it went like through the roof in the last years. Right? Why? Because there's huge demand for GPUs, right? For data processing, where we have to run these machine learning algorithms, and I don't think it's going to stop. I think if you look 5 years into the future, there's going to be even more demand, right? So how are we going to serve this if we are talking about trillions of dollars of investments? What are we going to just like double this every year? It's very difficult to imagine. So I think at some point we will have to start looking at other technologies. It's just inevitable, in my opinion, and I hope I'm right, because that's what our company is doing. Right? So hopefully, I'm not sure if hopefully is the right word, but I predict that in a few years we will struggle with analyzing the amounts of data that we have with machine learning and we will have to start moving to quantum. And at the same time, quantum will progress further. We will have, we will go from quantum calculators to slow quantum computers, and then we will be able to do even much more in quantum. So it will coincide, I think.
And typically, would quantum computing become obsolete if the internet didn't exist?
No. I think we would invent the internet.
Right, but if the internet just stopped existing, like all of a sudden, let's say there's no internet, then there would be no use case to use quantum computing because typically the data is in the cloud. And if there's no internet, there's no cloud.
Right, but we would figure out a way to send data.
Without internet?
Yeah, I'm pretty sure.
And that's a question I also want to ask, because could you imagine a world without internet or an upgrade to internet? Could you imagine?
No, not at all.
Not at all?
Not at all. I mean, I think if it fails, the internet, if it collapses tomorrow, we will have a new one very soon.
It's typically just servers. But can you imagine a world where we upgrade from servers to because technology is so advanced, we don't need servers for internet? Interesting. Also a graph problem, by the way, how to distribute compute. On edge devices and so on. Yeah. Right.
But not in the near future.
Not in the near future.
And I think we will have. I don't think the power of internet will go down. We might replace it, but if we do replace it, it will be something even more powerful.
Even more powerful, but still on servers, because that's what internet is.
On servers, at least for some more time,
yeah.
But when we have like really powerful phones, and then we can distribute,
then that's different.
All right, but
but not yet.
I don't even imagine that.
Did you hear recently? This is just off topic, but China rolled out these phones that can batteries that can last 50 years. 50 years. Did you hear about this?
No.
I don't know how it works. I didn't look into it, but it's a new technology. So the battery and probably the phones that they were going to develop on this battery can last for 50 years without needing to charge.
That's crazy.
Interesting. It's crazy, but I also think, in my personal opinion, what are the caveats to this? Does this mean that they can spy on me? What's inbuilt, and you never really know the inside of your phone. You just know the outside. You don't know what's inside it, and that also scares me.
Yeah, very interesting. I haven't heard of it. I don't know what to think about it. But
What would you say to an individual who is off the radar and is, for example, not on social media, but just doesn't believe in wanting to expose themselves, wanting to be around Wi-Fi, wanting to connect to Wi-Fi, owning a smartphone? What would you say to that individual?
I don't know how you can do it without. It's like we had this very interesting discussion in Las Vegas. I think it was. It was in Las Vegas, and it was about gaming. And so Las Vegas is encouraging children to game in a safe way. Right? So they do programs and they teach them how to be professional esports players. Right? And my first question was like, how can you encourage children to play video games? Right? This is insane.
Yeah.
And like just as a city. And their answer was, well, esports is here. We want it or we don't want it. It's here. We can either win in it or not. But the fact that it's here will not change. And I think this is a similar situation. Well, networks are here. Wi-Fi is here. This is not changing. You can either win in this setting or you cannot. That would be my take on it.
That's a good take. Good one. I love it. Okay, so then we're going to wrap up, and I want to know, just briefly, going into the future of TipQC, and you obviously have your colleagues coming. What are you building next? And maybe you touched on this already, but tell us, what are you building next that the audience can expect and hear from?
Well, first of all, we want to beat classical graph analytics and graph machine learning algorithms and have them our algorithms be faster, more accurate, better, and so on. So this is the technically number one goal. The second thing is we want to build use cases, like where do we apply these graphs, either for classical graph analytics like social media networks, recommendations, road networks, and so on, but also for machine learning on relational databases and so on. Right? And 3, just build the whole ecosystem, be active in promoting quantum, working with hardware providers, working with integrators, classical software providers, clients, and so on, to just advance the whole field further.
It's interesting because since you work B2B, and not so much the retailer, you don't really need a social media presence. Would you agree?
I think at some point you do. You know, like it can be. It's a difficult topic. It's a topic I struggle with a lot because we are a very technical team. We are physicists, we are mathematicians, computer scientists.
Right.
I don't particularly enjoy using social media myself.
Right.
But at some point, if you have a business, you sort of have to. It's really hard to survive without nowadays. So, yeah, we do use it.
In terms of LinkedIn, you mean?
Yeah, we use LinkedIn. That's it. And we have a web page. We should do much more. But you know, there's so many areas to focus on in a business, especially if you're a startup, and you only have that many hours in a day.
All right.
So,
right. I know the struggle.
All right.
I know what you mean. Martin, thank you so much for your time. Very insightful interview, and I really appreciate it. For those who don't know your company and would like to get in touch, what is the best way they can get in touch with you or your company?
Just www.tipqc.com, and my LinkedIn profile is Martin Vogrin, and TipQC should find it. Yeah. Other social media, I don't actually use that much.
No worries. Brilliant. Martin, thank you so much for your time.
Thank you very much for having me here.
Guys, ladies and gentlemen, hope you enjoyed this insightful interview on quantum computing. Definitely, I learned a lot from here. So please do check it out. And we will drop all the links in the description for Martin Vogrin and his company. Thank you so much for staying with us and following our page. And we will see you in the next podcast. So thank you so much and goodbye.